Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to look at the first category of solutions to MDPs called dynamic programming. Dynamic programming was pioneered by Richard Bellman, who also gave us the Bellman equations for MDPs. The Bellman equations allow us to define the value function recursively. You can see that if we multiply out all the terms in the Bellman equation, we actually get a system of linear equations, one for each state in the state space. Because this is a linear equation, we can actually solve for the value function analytically. However, because this is machine learning, we are more interested in iterative solutions. The first algorithm we looked at is called iterative policy evaluation. This is called the prediction problem. Given a policy pi, we would like to find the value function for that policy. Essentially, it's just repeatedly assigning the right side to the left side of Bellman's equation. Bellman's equation says that these are supposed to be equal. Therefore, when they are equal, that means the value function has converged. Remember that one of the tricks is that you don't have to calculate the next set of v's from the previous set of v's. We can just update them in place, which has the added benefit of saving memory as well. Next, we looked at policy iteration. This is also known as the control problem. The basic idea is that there are two main steps: policy evaluation, which we just talked about, and policy improvement. We do this in a loop until the policy converges, or in other words, doesn't change anymore. Policy improvement consists of finding the argmax over all possible actions from a state. Recall that policy iteration is inefficient. The outer loop is iterative, meaning we have to go back and forth between policy evaluation and policy improvement until the policy converges. But policy evaluation is also iterative, so we need to wait until the value function converges too. In other words, we have an iterative algorithm inside another iterative algorithm. The solution to this is value iteration. Specifically, we notice that instead of doing many iterations of policy evaluation, we only need to do one, and the algorithm still converges. Furthermore, we don't need to explicitly do the policy improvement step at all. The policy improvement step is an argmax, so all we need to do is put a max into the value update step, and we're effectively doing both policy evaluation and policy improvement at the same time. This idea of taking a max when updating the value function appears again when we look at Q-learning. Dynamic programming lays the groundwork for the other MDP solutions, but it's not very practical. First, it requires us to loop through all the states. This can be problematic since state spaces grow exponentially in size, and it doesn't help us at all when we have infinite state spaces. Second, it requires a model of the environment, specifically the state transition probabilities. As you can imagine, trying to estimate these over all states and all actions would be a difficult task. Lastly, notice how these algorithms don't actually require your agent to play the game. It's therefore not really learning from experience, as we would expect a reinforcement learning agent to do. As you know, Monte Carlo methods and temporal difference learning do learn from experience, and because of this, only update the value function for states that were experienced.